Start the recording. Sensation is the process by which we get information from the outside world into our nervous system. So how do we do that? Can someone explain to me, just if you were explaining this to someone who knew nothing, how would you explain sensation? What is that process?
So basically there's these things called sensory receptors, and each receptor is specialized for converting an energy source into an action potential, like vision into light, hearing into sound, and smell and taste into chemical. So it goes into different sensations.
Okay, good. So we have sensory receptors. And so you said that those sensory receptors, their purpose is to do what again?
So sensory receptors, so there's different receptors, and they're specialized for converting an energy source into an action potential.
Okay, good. And what's an action potential again? What is an action potential?
Is it like a change?
Not just a change. So it's a very specific thing in terms of the nervous system. Where are action potentials within the nervous system?
Is it in the nerves?
It is. What is it about within remember a nerve is actually like a cluster of neurons. So we're talking about in the neuron. What is an action potential within the neuron? So an action potential is just the fancy way of saying an electrical charge, that electrical impulse that the nervous system sends. Remember, that is the purpose of your nervous system, sending electrical impulses. So a sensory receptor is going to transform, it's going to take an energy source and turn it into electricity that your nervous system can understand. So think of it this way. What we're doing with sensation is we're trying to translate something. Sensation is the process of translation. The nervous system does not inherently know how to understand light. So remember that light is photons. You have photons are the particle of energy. Your nervous system doesn't naturally know how to handle a photon. When you see something, it's not like your nervous system is sending photons through the neurons. It's not sending the photons up into the brain. What it's doing is it's sending an electrical pulse, an electrical charge, that action potential that was generated by the photon, that was generated by that energy source. Okay, so sensory organs are collection. So sensory organs like eyes and ears and your skin, these contain sensory receptors, a bunch of sensory receptors that convert energy into an electrochemical impulse or an action potential. And so we have many, many different types of sensory receptors that are specialized for each of those types of energy sources. So I want to make sure we're, again, crystal clear on this. How would you describe how light is turned into an electrochemical impulse? How do you turn light into this electricity that is then sent through your nervous system? I'll start. It's in the eye, right? So the eye does it. How does the eye do that?
It focuses light on the retina, and the retina has cones and rods, which turns that into a signal for the brain to interpret.
Perfect. That's great. Yeah. So you've got the cornea, which is the very outside layer. You got that lens on the inside. Those are taking light in and refocusing it, putting it onto the back of the eye, which is called the retina. And that is where all the sensory receptors are, those rods and the cones. So those things are specialized for turning light, for turning photons into an electrical impulse. Then that electrical impulse gets sent up the optic nerve. Where does it end up?
And the visual cortex in the back of the brain?
Yep, back of the brain, visual cortex, the occipital lobe. Yep. All right, very good. Yeah. So the eye's purpose is simply to translate that light energy into an electrical impulse that your brain then understands. Okay, how do we translate sound into an electrical impulse?
The sound is vibrations, which like pounds onto the eardrum. There's 3 little bones in the eardrum that vibrates, and the vibrations are sent through the can't figure out the word at the moment, but it has fluid in it, and the fluid also vibrates, and there's little hairs in there as well that turns this vibration into an electrical impulse.
Perfect. Yes. And the word you're looking for is cochlea. So
Thank you.
that little membrane in there, it's just like a drum. It's just like a speaker. If you ever play music on a really large speaker, you play a song that has like a lot of bass, you can actually see the speaker move, right? It vibrates. It's like a drum that moves with the sound of with the sound of the song. Same thing with your eardrum. That's what it is the vibrations enter your ear. It causes that thing to vibrate, and depending on how it vibrates, that vibration will vibrate the bones on the inside. Those vibrating the bones will then cause the fluid inside of that kind of shell-looking bone structure, the cochlea, cause that fluid to vibrate. And then that fluid vibrating stimulates little hairs that then create electrical impulses that are sent into the brain. So again, we're trying to convert a physical energy, that kinetic energy of sound, of vibrations, into an electrical impulse, and that's how you do it. I don't know if anyone else was kind of surprised just how complicated auditory transduction is. And transduction is just another way of saying turning energy into an electrical impulse. So auditory transduction would be changing auditory energy, that the vibrations of sound, into electricity. It's really kind of fascinating just how many steps are involved in that. This is why hearing can actually be so sensitive. So potentially, it's easy to accidentally become deaf, because if you interrupt anything along the way, say if you puncture the eardrum, that it doesn't vibrate the right way. If those little bones inside of your ear break, if the cochlea is broken in some way or fractured, or that liquid is not in the perfect amount inside, or if those little hairs inside are not as responsive, any mistake along the way could actually interrupt your hearing, how you end up translating those vibrations into an electrical impulse.
And don't stick Q-tips down your ears.
That's largely why they suggest that. I mean, there are a couple of reasons. So one is if you kind of stick it in there, there is the potential for it to become, if it's too far in, to become infected. So that's a problem in and of itself. If you get an infection in there, the infection could then damage and break down the tympanic member, the eardrum. If you stick it down too far in there, what you could do is you could actually push against the eardrum and then accidentally rupture it. It's just a very thin material, so don't push that Q-tip too far. Or if you've got earwax in there and then you're pushing the earwax way up in there, it might get lodged against the eardrum. And so as the eardrum attempts to vibrate, it then has to vibrate while also having earwax pressed against it. That's kind of like if you've got a drum and you try to drum it, you just put your fingers on the drum and then hit drum it. It doesn't make the same kind of vibrations. It has that kind of dead kind of dull sound to it. Same deal. So anything that mechanically gets in the way of all those parts vibrating is going to get in the way of your ability to hear something, because you're not able to transduce or translate the vibrations into an electrical impulse. Okay, how about taste? How does taste work?
So the taste buds are the sensory receptors, and the papilla, I don't know if I'm saying that right. The bumps on the tongue are basically get the taste sensations.
Good. So when you eat something, your saliva breaks it down. The chemicals within that food seep in between the papillae. Yeah, the papillae are those bumps. And so in between each of those bumps, you have a little crevice. It gets in there. The chemical is then detected by the taste buds, and the taste buds translate it into an electrical impulse. Again, we're taking a chemical energy, that kind of energy contained between the bonds of whatever you're eating, and turning it into electricity. Okay, and so then we have the same for touch as well, right? So when you touch something, there are many different kinds of touch sensation. You can have pressure, you can have texture. Pain is a touch sensation. In each of those cases, you are translating some kind of energy source into an electrical signal that gets sent through the rest of your nervous system.
I did have a question about like the touch and whatever. I think in the video you mentioned, and my memory's kind of hazy, but you said something about like pain and the like excitement sensation or whatever. But what about some people who are, say, sexually aroused by pain?
So that's actually a good question. I really like that question, because so with that, what happens is so you're probably talking about the gate control theory of pain. And that's the idea that if you actually experience pain, your body will at first experience pain, but then because pain is just a warning system, it's something that you should feel, and then it usually should go away after you are aware that something has happened. Your body has no need for the pain anymore. And in fact, it could be a bad thing if it continues to feel the pain. So what your body will do is it will naturally produce what are called endorphins, which we've talked about once before when we talked about a type of neurotransmitter. An endorphin is the neurotransmitter that's responsible for dulling pain, for getting rid of pain. So when you feel pain, there's that immediate, I hate it, that hurts, but then it kind of dulls down and it goes away. The reason it dulls down and it goes away is usually the body starts producing endorphins, and the endorphins dull the pain. And it just so happens that endorphins also feel good. So one of the things that people can do is say you can submit yourself to something that would be painful, and you don't really like the immediate feeling, like, because it's painful, but then you might start to really enjoy what happens afterwards. You enjoy that endorphin rush. That's what happens with a lot of runners. Runners tend to get actually addicted to running. They can get the feeling where, say you're like a marathon runner, okay? Someone who enjoys running for practice, you might run 8 miles a day or something ridiculous. And what you find is that, a lot of people, when you start running, it starts to hurt, you hate it, you get like down the street and you start running out of breath, and you're just like, no, I don't want to do this anymore. Well, people who condition themselves to run a lot, what they do is they get the same pain signals at first, but then their body starts to expect it. They actually expect the pain. And so the body, what it'll do is it'll start pumping out endorphins ahead of time. So that most conditioned runners, when they start running, they don't really feel the pain anymore. What they do is they feel the immediate endorphin rush from their body pumping that out to suppress the pain. So, I'm actually in class. So you get that endorphin rush, and in terms of feeling, possibly getting sexually aroused by actually enjoying pain, it may actually be enjoyment of those endorphins that come afterwards. As much as if you're a runner, you enjoy running because you actually enjoy that feeling of endorphins. Does that make sense? So it's not the pain that you like, it's what that pain causes, the endorphin release.
Yeah, that makes sense.
Yeah, that's a great question. Pain is such a really interesting thing. This is actually, we'll talk a little bit about we'll talk a little bit about heroin and different kinds of opioids when we get to the chapter on consciousness. But one of the reasons that heroin tends to be so addictive is not just that it produces dopamine, which is the neurotransmitter that's primarily responsible for feeling good, for feeling pleasure. What happens is it also mimics that pain dulling sensation, the endorphins. It mimics endorphins. So not only do you feel good, but you take away the feeling of pain. So you're kind of getting a double dose of really good feels. You're feeling pleasurable, but you're also not feeling the bad stuff. And so compared to other types of drugs of abuse, that's why heroin tends to be so addictive. So and easily you can easily get addicted to it. Is you're kind of getting you're getting two benefits there, so to speak. Yeah. Great question. All right. So we're converting energy into electrochemical impulses, into those electrical impulses. So if we take what we know and we run through kind of, okay, we've just picked up a sensation. Light has entered your eye and you're sending that electrical impulse. Well, that electrical impulse gets sent through a series of neurons, right? And as it's being sent, it creates it releases those neurotransmitters into the synapse, which causes some cell next in line to do something. And because those neurotransmitters are being released, the neurons undergo long-term potentiation, which is when you stimulate a connection over and over again, it becomes stronger, more reliable. And as connections become stronger and more reliable, you can start to create these networks of neurons. And those networks are what gave rise to memories. And so what you're creating when you string bunches and bunches and bunches of neurons together is you actually start to create regions, you start to create clusters of those networks, of those neural networks that are then responsible for very specific things. So in terms of sensation, when the book says, when I mentioned that you create when you have something like a primary visual cortex, what that's referring to is a section of the brain where there are a bunch of those memory connections, a bunch of those neural connections that are specifically dedicated to processing the information that you get from light, from your eyes. So you're kind of building these many connections from birth, and so when a brain develops, you're developing those connections. When you look at this thing, I mean, it looks a brain. If you've ever seen a brain in person, if you've ever like dissected something and looked at the brain, it's very smooth and it doesn't look like a bunch of neurons, but that's what we're looking at here. Is any given part of the brain is just a really fleshed out, really dense mass of interconnected neurons. And each part is dedicated to something. So over here in this blue area, this is the primary auditory cortex. So a lot of the information that you hear is going to be sent here and then processed, and then it's going to be made sense of somehow. And right here you have what's called the somatosensory cortex, which we went over back in chapter 2 on biology, or chapter 3 on biology. This is where you get a lot of touch sensation. So a lot of touch sensation ends up being processed here. Smell tends to be kind of localized in here. It's kind of underneath. Smell is actually a much more basic, straightforward part of the brain. And so there was that, excuse me for all the coughing. There was that part of the brain called the olfactory bulb that's responsible for it. So you can't see it here, but that is a cluster of neurons dedicated to processing that kind of information. So that's what we're doing. We're taking in information, we're sending it to the brain, and then the brain does something with it in each of these specialized areas. All right. Now the big question remains, we're getting all this information into the nervous system, into the brain, but now we need to figure out, how does the brain organize it? How does it make sense of all this information that's coming in? So you're getting, you're getting visual information from light and auditory information from the vibrations in the air, and you're getting, taste and smell information from the chemicals and the things that you eat and the things that you smell, and touch sensation. All of these electrical impulses are arriving at the brain at the same time, and the brain's processing it at the same time. So then it has to make sense of it. Well, how does it do that? I want to introduce a concept that is not unique to psychology. This is a concept that you probably won't hear in like an introductory physics or biology or chemistry class, but if you go on to more advanced stuff, you'll probably learn about the concept of emergence. I don't know if anyone has heard of emergence before in any context, but here's the definition I want to give you. This is when an entity, something, is observed to have properties that its parts do not have on their own. So properties are behaviors which only emerge, they only come about when the parts interact within a wider whole. All right, digest that definition for just a second, and let me give you some examples of that. I think the best, one of the most basic examples of emergence that I could give you would be if you look at how atoms behave. So we know that atoms are all around us. They make up everything. If something is made of matter, it's made of atoms, right? My hands are made of atoms. The air is made of atoms. The walls around you, your computer, everything is made of atoms. So atoms are what give structure to our physical universe, right? Well, let's think about how atoms combine, all right? Let's take a very simple, you've probably learned that salt is made up of two atoms of two different kinds of elements. You have sodium, and you have chlorine. Now, if you were to eat, so if you put sodium and chlorine together and you bind them together, you get salt. Salt you can eat. But if you were to eat either of those individual elements by itself, it would kill you. Sodium by itself is poisonous. Chlorine by itself is poisonous. That's why if you got chlorine for your swimming pool, you don't want to inhale that. You don't just want to open the bottle and go, oh, look, it smells like chlorine. It's toxic to inhale. You don't want to do that. Same with sodium. You get raw sodium, it's actually highly flammable. That thing you can light it on fire super easily. But you also don't want to ingest it. It's poisonous. So it's kind of funny that if you take these two atoms that individually are poisonous, and then you put them together, that suddenly they make this extremely non-harmful table salt. What you could say is that by putting those atoms together, you've created an emergent property. That emergent property is table salt, that kind of salty, delicious taste that is actually quite good for your body. So you've now observed that an entity, salt, has properties that its parts, sodium and chlorine, do not have on their own. You've put together two things that created something entirely new. You could say the same about everything else. When you look at a person's face, you don't see their face as a collection of atoms, right? What you see is, you might see two eyes and a nose and a mouth, and you see hairs that make up a person's beard and mustache, or the atoms that make up their glasses or whatnot. By stringing together a bunch of atoms that make up the face and everything that's responsible for make a face look like a face, what you're getting is something totally new. You don't see atoms, you see a face. Faces are an emergent property of stringing together a certain type of atoms in a certain way. Right? So emergent properties are kind of everywhere. They're all around us, right? Whenever you see something and you kind of perceive this is a phone is really and something that's emergent from putting together a circuit board with a piece of glass on the front, with probably a case to protect it all. Each of those individual parts are not capable of accomplishing what a phone altogether is able to accomplish. So the phone is emergent from you combining these different pieces of the phone. If you think about animals and how animals interact, and ants I think are an excellent example. An ant by itself is capable of certain things. It can find food, it can eat that food, it can probably find some kind of housing, it's able to move its little pincers around, etc., etc. By itself, an ant is certainly capable of many things. But if you put a bunch of ants together, they are now capable of doing things in a colony that they are not capable of doing otherwise. For example, ants, when they're together, first can reproduce, right? An ant is not capable of reproducing itself. It needs to combine its genetic material with other ants' genetic material, having sex with each other. Ants, when they get together, are able to create actually these very complex societies. Turns out ants have really sophisticated ways of communicating with one another. They'll leave scent trails that other ants can then follow. So if there's a really large source of food, or if there's some kind of predator that they together need to overcome, they can lead each other with these scent trails and gather this food or overcome or battle this predator in a way that they otherwise wouldn't be able to do. Ants can actually, depending on the species of ants, when they swarm certain animals, they can kill those animals. Anyone who has ever stepped on a fire ant hill knows how effective ants can be in large groups together, right? You get one fire ant on you, maybe it bites you and it's not so bad. You get enough fire ants on you, they swarm your body and say they can get everywhere across your body. That can cause some serious medical issues for you. So together, an ant colony is capable of doing something that individually the ants cannot. Therefore, a colony is an emergent property of putting a bunch of ants together. Then we can also talk about people in the same way. Individually, people are capable of some pretty cool stuff, but the reason that humans have been able to, just spread across the world and to create the sophisticated technology and the innovations that we have is because we work together, right? A person by themselves can do some cool stuff, but if you get people together, you can create societies where people are specialized to do certain things, right? Where you can create a town. A town includes not just a person who's off, maintaining their own garden and perhaps, purifying their own water and all this stuff. When you get people together, now people can kind of specialize into, okay, these are the people that are responsible for running the water facility. These are the people that are responsible for running the government. These are the people responsible for volunteering at the fire station. And so a town is capable of accomplishing so much more than any individual could. So societies are an emergent property of putting a bunch of people together. All right, as much as anything can emerge from these things being put together, that is the argument here with neurons. Your neurons, by individually, can send electrical impulses, and that's pretty cool. But just by itself, a neuron is not going to accomplish much. It's only when you string a bunch of neurons together that they start to be able to do some really, really cool stuff. By putting neurons together, for example, by combining visual information with auditory information, with that chemical information, with touch sensation, by putting all these things together, you can create something that individually they don't create. And that is what we're going to call perception. And that'll be the second half of our chapter. So together, these neurons are capable of creating this kind of feeling that, I should say, the neurons are able to create this feeling that you are kind of present, that you're having an experience. So let me give you a much more solid example. When you're listening to me and you're trying to make sense of what I'm saying, you are at one time, I am speaking, which is auditory information. I am giving you this slide, which is visual information. I'm also sitting here and I'm kind of moving my hands around. That's visual information. You might be writing in your notebook, which is tactile information. So what you're doing is you're combining these different sources of information, the visual, the auditory, and by combining them all together, that creates some kind of perception for you. That creates, you've now, say, you now understand something about psychology that you didn't understand before. You have that knowledge, you've created that memory because you're combining these different sources of information all at once. That's perception. So what I'd like you to keep in mind as we go into this next week is that I think it will be helpful to view perception as an emergent product, an emergent property of all the sensory processing that your nervous system is doing at any given moment. So when you, when it's your birthday and you go home and the lights are all off and they all turn on and everyone's there and they say, surprise, you have this experience of happiness, of surprise, of glee, of like looking forward to the night. That's a perception that you have. That is an experience that your nervous system is creating for you. Well, if you really break that down, what's creating that is a couple of things, right? You've got the visuals of all your friends being there. You've got the auditory of them kind of like saying happy birthday, and all their faces might be smiling. And so you're getting information about their happiness as well. There's a lot that you could really break down that experience of, oh my God, it's my birthday and you're all here and I'm so surprised. You can break that down into many, many, many different sources of visual, auditory, tactile, etc. information. So that's what we're going to try to do. We're going to try to describe how does your brain take individual bits of information and put it together and try to make sense of it. Perception is the process by which we try to make sense of sensory information. All right. Thoughts or reactions to that? I know there was a lot in there. It was kind of convoluted, but I hope that the idea of emergence landed well. Does that idea make sense, the idea of emergence? Or do you find that helpful for understanding how you kind of get from neurons to you having an experience, or you kind of having this kind of conscious experience that you're having right now?
I do think the examples helped.
Okay, good. This is one of those things that I think you're going to have to sit with, and you're going to have to get into the next week's content to really put it all together. I think that the idea of emergence is not something that's very intuitive. However, if you think about how the brain is designed to make sense of and put together all this stuff into this kind of emergent experience that you're having, I think it's going to help a lot. So kind of keep this in mind for the coming week. Yeah. Okay. Well, like I said, this discussion was going to be a little bit shorter. This is all I have for you guys. What I'd like to do, though, is I'd like to encourage you, if you have not done the research participation requirement, work on that. This is about 30 minutes that you wouldn't otherwise have. You could get at least one study done in 30 minutes, I assure you. So use this time for that. If any of you have questions about just anything related to the class. I want to make sure, some of you, I think, may have submitted the research proposal, but then I emailed back saying that it wasn't formatted correctly. Just make sure that you're all checking your email, that you get those messages, because I think there are just a few outstanding research proposals. Make sure you get those in ASAP. Other questions, concerns before we break for now?
I have a question about last week's exam. I went to take it earlier and it was not in Blackboard, so I don't know if I missed the time limit. It was like 11 something when I went to take it.
Which one, for chapter 6 or 4A?
4A.
I was about to ask the same thing.
Wait, so it wasn't there at all last week?
I didn't see it this morning.
Yeah, I went to check this morning. I sent you an email about it, but I've assumed you've been busy most of the day.
So this morning, it would have closed at, oh, did it close early? Let's see. It's possible that it closed earlier than it should have. Let's see, 5, 6, A. Ah, yes, I see what happened. It closed a little bit earlier than it should have. So what I'm going to do, that is my mistake, I'm going to open this for another day. I apologize. Everyone will have until tomorrow at 5 p.m. to complete it.
Thank you.
It should now be available. Yep. Yeah, I had it set to close at 9:30, which is when my other class closes. So yeah, you got a little bit extra time there. I apologize for that. Thanks for bringing that up. All right, other questions, concerns? All right, well, thank you all for being here, and have a wonderful, yeah, Emily, what's up?
I got a question because I sent it to you my proposal, but I don't know. I tried to I'm still working how to use my computer, so I tried to copy and paste my document to send it to you for Word. But I don't know what I did, but I think I deleted and I don't got copy.
Oh
So
no, okay.
yeah, so I'm trying to looking for it, like if I got something. But like you can send me the document because I tried to go into the Blackboard to get my document, but I can't do that. I don't know why.
Yeah, so there is something submitted, but it's a .pages document, and I'm not sure how to read. I'm not sure how that was submitted. What I could try to do is download that and send it to you. But
Okay.
so what did you have it written in that you first submitted it? Like
What?
so the first time you submitted it, in how did you have it saved? Like how did you submit it? If not in a Word document.
I just get in proposal on research one and use put it over there my document like.
Like in what program did you write it in?
It's for I don't know. It's for the Mac. So
Oh, for
probably
Mac. Okay. Oh, so maybe Mac has its own. Let me look something up real quick. I'll look into that. Give me a second. Oh, I see. Yes. Yeah, the .pages document is for Mac. So what I'll do is I'll download it and I'll send it to you, and chances are you'll be able to open it on a Mac. I can't open it. I'm using a PC. So open it up, and maybe then if you can, try to copy and paste it into a Word document and resubmit it.
okay.
I'll send it actually right now. Give me 2 seconds.
And I got another question. I already did. Oh, I already did my online participations. Like I did two. So I have to send you like a picture on my screen for email.
Sorry, you already did two. I didn't. What about a picture?
Oh, I say I already did my two online participations. So like
Yes. So you're good with those.
yeah, like, so I just have to send you the picture with the random number for email.
Yes. Did you get those codes at the very end? Did you kind of see there was a page that said, copy this, send it to your instructor?
Yeah.
Yeah, just take it, either just highlight it, copy and paste and send it to me, or take a screenshot of it and send that screenshot to me. Either of those would work. As long as I get that number, there's like a 6-digit number that came with it. I need that number.
Okay. Yeah, like the random ID number, right?
Yep.
Yeah.
If you can get that to me somehow, that'll suffice. That'll be enough.
Okay.
Oh, and also which study it was. So you know how it says like F18 number 4. I'll need that as well.
Oh yeah. Yeah, I got it. Um,
Okay, I just sent the research proposal to you. Let me know if you are able to open that up.